I'd like to go over the types of data that we discussed in the lecture section of this week's coursework. There are four basic kinds of data types that we're going to be working with, and it's important that we understand these data types because it's going to affect the types of analyses that we're going to wind up doing. One form of data is nominal or categorical data. A lot of these things have a number of names or references depending on the situation that you're in. SPSS kind of restricts these to three types of data types that it summarizes them as. Okay, but one type is nominal data. That's basically, as it would suggest, a name. For instance, could be gender, male or female. Could be hair color, brunette, blonde, redhead, and so on and so forth. That's typical of nominal data. Okay, ordinal data is categories, but the categories have some order. For instance, they could be a grading system like poor, fair, good, and excellent. Okay, we know that that's a name. Each one of those things is a name or a category: good, fair, poor, and excellent, so on. Right? Those are categories, but those categories have an implied order. So that would be called ordinal data. Another good example of that is the pain scale. If I ask you what level of pain, or you might ask a patient what level of pain they're experiencing on a scale of 1 to 10, well, they might say 3, or they might say 5. They might say a category, and you would understand that that number represents more pain or less pain. But there's no universal agreement on what 6 represents. 6 might be one thing to one person and another level of pain to a different one. And the difference between 3 and 4 might be different to a single patient even than the difference between 7 and 8. There's no way really to quantify that the scales are even or equal in that regard. Okay, so that kind of data where it's categories but they have order, we refer to it as ordinal data. Okay, so now the next type of data that we like to talk about, if I go down to the bottom here, is numerical data, also called continuous data. That's any data that's on a continuous numerical scale. Could be blood pressure, could be age, could be weight, and so on and so forth. Any numerical data that has a scale. Okay, so sometimes when that numerical data is an integer data, for instance, the number of siblings that you might have, right? Might be 2 or 3, or if you have a large family, 9 or something like that. But it's going to always be an integer or a small integer. That often is called numerical discrete data, or just discrete data. Okay, so we have nominal, continuous or numerical, we have ordinal, and we have numerical discrete data, where we're talking about a small integer. Now, SPSS really only deals with 3 versions of that data: nominal, ordinal, and anything else it calls scalar, or it refers to numerical data as scalar data, as you'll see when we're working with it. Okay, so we're often dealing with either populations or samples. In statistics, we're rarely dealing with the actual population because, in general, there's just too many people for us to get complete information about. Okay, so often we're dealing with statistics. Okay, now there's various kinds of representations for statistics associated with populations versus samples. For instance, the mean of a population is called mu. The statistic for the mean of a sample is called x bar, okay, or x with a bar over the top of it. Notice one uses a Greek letter, the other uses an English notation. Okay, the standard deviation for a population is called sigma. Standard deviation for a sample is called standard deviation, or SD. The various other kinds of variables are represented differently as well. There's a chi-square function, and so on and so forth. Now, you may notice that I use the term parameter, mu, sigma, and so on and so forth, when I talk about population, and I use the term statistic when I talk about samples. So we want to remember that distinction as well. Okay, we like to represent this data and organize it into tables. Okay, so here you can see a representation of some frequency tables, a number of people within a bunch of different categories. Okay, we also like to organize data in terms of charts because charts make the data a lot easier to interpret at first glance or easily. So for instance, here is some nominal data represented by frequency. The y-axis is the frequency, the x-axis is the category or name. Okay, and this happens to be hair color in this state. And these types of graphs are called bar charts. This or column charts in this case because the bars are vertical, but really basically the same thing. Okay, here's another kind of bar chart, whiskey bar chart or candy bar chart, and of course the ubiquitous sushi bar chart. That's as close as we get to jokes and statistics, so I'll move on from that. Another kind of bar chart that we see, or column chart that we see, is called a histogram. Histograms are like bar charts, but instead of representing nominal data, they're used to represent numerical data. So for instance, this chart represents the heights of people in a sample. So we can see that in the first bar, that there are 6 people that are between, it looks like 139.5 and 149.5 centimeters in height. And the second bar that contains 9 people between 149.5 and 159.5 centimeters in height. And notice what's happening here. Each person that's within that range is represented by the height of that bar. Now these ranges, unlike the columns in the bar charts, which would represent nominal data, touch each other. They're adjoining one another. And that's because there's no gaps between them. In other words, if a person's height is 149.4, they're in the one bar. If they're 149.6, they're in the next bar. Okay, in other words, there's a continuous number scale here that determines where a particular person would fall. And that's typical of something called a histogram. Okay, what is this? Bar chart or histogram? If you said bar chart, you're right. How about this one? Bar chart or histogram? If you said histogram, you're right. Notice that the bars are, the columns are connected and they represent a continuous value for the weights of lambs in this case. Okay, we also like to summarize data using something called box plots. Now these box plots are summaries of the values of all the individuals in a collection of statistics. Okay, you can see a adjoining bar chart box plots on the left where you can compare different samples. For instance, the amount of sunlight that's received by different types of trees and so on and so forth. If you look over to the right, you'll see one of those box plots isolated. And if you look carefully, the diameter of the trees in this sample are represented by the box plots, that red box plot. Okay, and you'll notice that that there are 2 lines that extend from the middle of that box plot with little horizontal tick marks at the top and bottom. They represent the minimum and maximum value for that sample. So the trees in this sample were between 12 inches in diameter and about 18 inches in diameter. Okay, the bar in the very middle at about 15 represents the median tree diameter, about 15 inches. That's the middle value for all of the trees. Okay, now the red box itself, the bottom of the red box represents the 25th percentile. In other words, 25% of the trees are smaller than that value and 75% are greater. And the top of the red box represents the 75th percentile. In other words, 25% of trees are greater, 75% of trees are less than. So that means within that red box are the middle 50% of the trees in terms of diameter. That's also called the interquartile range. You'll notice there's a red dot up there by about 24 inches. And that is a tree that is much bigger than the rest of the sample. And it's displayed here separate from the bar chart because it's so much different that we're wondering maybe that data is not correct or maybe there's a problem with that data. or that point, maybe it was incorrectly entered, because it's so much different. We call that an outlier. In this case, that dot represents a value that's so much greater than all the other trees in the sample that we consider it might be an outlier. Okay, so we also have scatter plots where basically each one of these values represents the X value represents a person's age, and the husband's age, and the Y value represents a wife's age. You'll notice that for the most part that the age of the husband has some relationship with the age of the wife. As the husband gets older, wife gets older as well. Okay, so graphical display of data is important to us because it helps us understand the data. I'm giving you a link also in this segment on Blackboard to a YouTube video, which is actually a TED presentation by a Professor Hans Rosling that has some very impressive use of graphics to demonstrate some sophisticated statistics. And I'm hoping you'll take the time to watch it. It's pretty impressive. Try and look to at least the first 7 or 8 minutes of it. It's a little longer than that, but the first 7 or 8 minutes are pretty dramatic. Okay, we're going to be doing a little bit of hands-on practice with Excel as we get through this. Then we're also going to try out our hand on SPSS. And I'll leave it up to you to do your own work on R if you decide you want to work on that as well.